This question is taken from the ENGAA 2020 Section 2 paper, and it is question 20. So we read, a cell has EMF E and internal resistance R that varies with current I as R equals K I squared, where K is a constant. A variable resistor is connected across the terminals of the cell. Which expression gives the resistance of the variable resistor in terms of K and E that causes maximum power dissipation in it? So how do we find this resistance that maximizes power dissipation in the variable resistor? Well, whenever we have questions in electrical circuits, and whenever comparing things or trying to maximize, we have to try and make use of the constants that we're given. So we should try to involve these, so the E and the K, and all the things that we know are constant. So if we're trying to maximize power dissipation, what is an expression that we can use for the power that we can see how it varies with another quantity? So we could say that power in the resistor is EI. This is a total power from the battery, taking away whatever power is dissipated in the internal resistor. So this is I squared times R. We want to maximize this power dissipation. So dP by di should equal 0 if we want to maximize this. And then if we differentiate this, we get E minus 4k I cubed equals 0. So I equals E over 4k to the power of 1/3. So notice how we used I instead of using the resistance of the variable resistor in order to calculate maximum power dissipation, because any expressions we had involving the resistance would have also involved internal resistance R, which will vary with the current as well. So it's best to vary everything in terms of the current and what we know. Then how can we relate the power to the resistance of the variable resistor? Well, this is P equals I squared times R max equals EI minus K I to the 4. This involves the current that we have just now deduced. So to get R max, we divide by I squared, so we can take a factor of I out, and then we get E minus Ki cubed over I. And then the reason for doing this, rather than getting just E over I and then Ki squared, is the fact that we can make use of the fact that I is to the power of a third, so E to the power of a third. So keeping a cubed term in here will make it easier for the algebra. So we have 3e over 4, because Ki cubed is equal to E over 4, so we get this fraction on top, and then this is just our expression for I, so E over 4k to the third. Now the answers give options in terms of a constant or a number times something to the power of a third. So it'd be good to get every one of these quantities on the numerator and denominator into a power of a third. So we have to take the 3 out, and we can get the E cubed over 4 cubed to the power of a third, and then E over 4k to the power of a third remaining on the bottom. So we get E cubed over E is E squared, and then now we get a 4 over 4 cubed when we move this over here, and the k on top as well. This now gives us an expression of 3 times k E squared over 16, which is the 4 squared. And this is all to the power of a third, apart from the 3 on the outside. This is the expression for the resistance that gives the maximum power dissipation. So the main principle to use in this was to try and involve the things we know as constant, because if we tried to work everything out just in terms of resistance, which is what we ultimately wanted, we would have had to involve the internal resistor that varies with I. So it's best to just vary everything with the current in the first place, and then substitute that into our expressions.